Should I start now? Or should we give them a couple of minutes more? All right, let's get started. Thanks for joining this lecture today. Today I'm going to talk about the automatic speech recognition, which is what I'm working on in Gridspace. Today we are going to talk about a briefly history of the automatic speech recognition. And also I'm going to explain what is ASR problem. And also we're going to kind of review the kind of the conventional ASR system, which is HMM-based ASR. And also we are going to cover end-to-end ASR, which is kind of the modern ASR that a lot of industry or researchers are interested in. And also we are going to talk about the further improvement over the end-to-end ASR system. All right, history. This is the first speech recognition system. It was 1952, Bell Lab Audrey system. At the time, it can just recognize just digit. Surprisingly, it has almost 90% speech recognition accuracy, but it only recognizes the inventors, the researcher's voice. It cannot recognize any other people. 10 years later, IBM invented the IBM shoebox. It can recognize some arithmetic comments like plus or minus, total, and also it can recognize digit. So basically, it can do like 3, 5, 4 plus 4, 3 total, and then machine can kind of do some simple math calculation. Yeah, but you know, this is not really fascinating that we are wanted to have, but at the time it was really surprising invention. At the time, it was not digital kind of computer-aided system. It is mostly like analog system that use circuit and then to find what's the template of that each word, and then it kind of lamp up the digit, each digit. That's the system. And since starting 1971, DARPA started the research program to accelerate the research on the speech recognition. The mission of this program was to recognize the more than 1,000 words. That was the mission. At the time, the Carnegie Mellon University, with Harpy system, it was able to recognize the more than 1,000 words with this system. At the time, it was using beam search based on the template-based matching, and yeah, it was very kind of the new beginning of the ASR system. And after then, around the 1980, there was a lot of research going on, especially at the time the people are using hidden Markov model system. They have seen a lot of the improvement for the speech recognition task. Also, at the time, everyone should know that Geoffrey Hinton or other Alex Weibel. They are very kind of pioneer of the deep neural network. At the time, they tried to recognize phoneme with the time delay neural network, and yeah, it was amazing. And over the time, people are working on to make the more robust ASR system. Around 2000, NSA started using the speech recognition system to find the keyword they are interested in from the humans recording. But even though some government or DARPA or like military, they're interested in using the speech recognition system, but it didn't draw the public attention until 2010. At the time, have you you remember that some of people you remember that the 3 came out in 2011. Yeah, at the time, yeah, it was really amazing. Machine can understand what you're asking, and then it can answer to its voice as well. Since then, yeah, there has been a lot of the application of the voice assistant system, Alexa 3, Google, and Cortana, and so on, a lot of system. But behind of this success, there was neural network. Since kind of around the early 2010s, yeah, people started using the deep neural network in the speech recognition system, and they have seen a lot of success. And yeah, so now we are now in 2023, and yeah, it's amazing. Now people may have live in a lot of machine that actually does the speech recognition system. Okay, so we are now diving into the ASR problem. So before diving into the mathematic formulation, I want to kind of give you some wave file, and then you hear that this wave file, this speech, and then you try to guess what the speaker is saying. Let me play.
If you would still find it.
My email address is emarshall@yahoo.com.
Let me repeat again.
If you would still find it.
My email address is emarshall@yahoo.com.
Is there anyone who can guess what they are saying? Francis?
My email address is issue@yahoo.com.
Your word error is around 50. Thank you, Michael. Anyone? Let me repeat again.
If you would still find it.
My email address is emarshall@yahoo.com.
Yahoo.com. Almost there. Yeah, pretty good ASR system. All right. So how we formulate the ASR problem? So as you hear, you will hear some kind of noisy version of what people are saying as a waveform. People are actually in this example. He was saying that my email is marshall@yahoo.com, but with a lot of the sound generated by people can be very different from people to people. Also, it can be very different in acoustic environment that you are in. So anyway, you're given the noise observation, and we say that there is a channel, and channel kind of transform the actual what people are saying to the sum of the noise version of the waveform. And then in speech recognition, you have to guess what the speaker is saying given your observation. So that's the problem. Anyone have any question? All right, so this is a high level of what speech recognition task is. Okay, let's go deeper more with the mathematical formulation. So here, in speech recognition, you want to find W, the word sequences, most probable word sequence that maximize P of W given X. Here, X is your observation, the waveform. So when you're given the observation, you want to find the most probable sequence. With Bayes' rule, you can kind of flip around the P of W given X to P of X given W, multiply P of W, divided by the P of X. And here, you want to find the most probable word sequences. So P of X in denominator actually is not needed. So we drop, and then the problem that you want to find is we want to find W that maximizes P of X given W multiplied by P of W. Everyone is good? P of X is nothing with the W. P of X is always kind of the constant. Yeah, signal. Yeah. All right. We want to talk about the X. X, what you hear here is actually waveform. But actually, this is the waveform that you actually hear before. But you cannot guess what this kind of this signal means, right? It's very hard to distinguish, or it's hard to extract the actual word sequences from out of it. Yeah. So what people does is like apply Fourier transform to analyze the signal in frequency domain rather than time domain. The benefit of the frequency domain analysis is give you some more kind of the intuitive way to think about what the phoneme looks like. And then here there is a 3 vowels: I, U, A, U, E, U, A. And then each vowel has different kind of the frequency pattern. Usually the most kind of the spectral peak at each phoneme, we say the formants. So each vowel has different formant here, and the F1 is the most dominant formant. The F2 is the second dominant formant. With kind of that, you can kind of the model that what is how phoneme looks like with in the frequency domain. All right, so now you are getting the what the benefit is within the frequency analysis, right? But you know, the speech is continuous, and most often you are pronouncing multiple phonemes when you speak. So we have to kind of find the kind of temporal variance of each phoneme, each frequency pattern, to find out each phoneme in the speech signal. So rather than just using the normal Fourier transform, we used short-term Fourier transform, and which means that you kind of select the kind of shorter region, and then you apply FFT, and then this is kind of your each kind of the frame of the signal that you want to kind of guess. And once you apply this short-term Fourier transform, you will have this kind of plot when you kind of use magnitude of the short-term Fourier transform. So here you see in the frequency region, each has different amplitude in the signal, and then based on that, we kind of the machine tries to find which kind of the phoneme or which word sequence is conveyed in this signal. And moreover, the short-term Fourier transform, people are looking at the human auditory system, and what they found is people are more sensitive to lower frequency region than higher frequency region. For example, there is 3 pairs, total 6 sounds of the sine wave, and each two are spaced with the 500 hertz. So I will play that. This is 500 hertz. You can easily see the difference between the first one and second one, right? Those are 500 hertz and then 1000 hertz. Next one is this is the 5500. And next one is this is 6000. So even they are spaced with just 500 hertz, same as did before, but they sounds very similar, right? Next one, be careful. Next one is the this is 10,000. Yeah, this is the 10,500. Yeah, you don't kind of it's hard to kind of tell the difference between those two. So inspire this kind of the human auditory system. When people are making some filter, they kind of, okay, let's try to make some other processing that really does similar to a human auditory system. So they applied some MEL filter. So they have more kind of receptor in the lower region, and then kind of fewer receptor in the high frequency region. So they apply. So we call this is MEL filter bank, and then once we apply the MEL filter bank on top of this short-term Fourier transform, we will have this kind of diagram. All right, so this is what actually we are using for speech recognition system. Rather than using the time domain signal, we're going to use this X MEL spectrogram. Do you guys have any question? Yeah.
Why is it called a filter bank?
I haven't thought about it. Do you have it? Do you have an answer?
Yeah, I think there's a lot of say processing algorithms as essentially filter sequences that run in parallel. And so the MEL spectrogram, which is obviously a scale variant of the FFT, can be implemented as a filter bank.
Thank you, Anthony.
Also, just a reminder to like repeat questions into the microphone.
Thank you. All right. Now we are going to go over the HMM-based speech recognition system. What is HMM? HMM is the statistical model of the Markov process. Markov process, the current state is only dependent on the single previous state. That's the Markov property. And the stationary in the Markov process is transition probability doesn't change over time. So it always have same kind of transition probability. And then as HMM, as Hidden said, we don't typically have the access to the state, but rather than state, we are getting some observation. With observation, we are trying to guess and estimate what the current state is. So that's the HMM system. And let me give you some very simple example. Here, this is the two-state HMM. So, for example, my wife always start a day with either happy mood or bad mood. All right. So with the 0.8 probability, she starts a day with the happy mood. But 0.2 probabilities, she can also start with the bad mood as well. And she can keep staying in the happy mood, or she can also, sometimes later, she can be in bad mood as well. as a husband of my wife, I have to guess my wife my wife's mood is. Yeah, to live a happy family, happy life. But my wife doesn't tell me the her mood. She only sent me a emoji, smiley face or frown face. And whenever I got the emoji, I should guess what's her mood is. So yeah, basically, if I start a day with the smiley face sent from my wife, then I can safely guess that, oh, a pure happy mood given by smiley face is definitely higher than pure bad mood given the smiley face. So I can safely guess the, oh, she is happy now. I'm good now. But if she keeps sending me emoji like smiley face, frown face, smiley face, frown face, then it's very hard to guess, right? Then you have to do real math. Yeah. So this is going to be your homework, and after this lecture, and also you can kind of refer the what is the hidden Markov model, and then what's the how to calculate the state propagation. And with speech recognition, how we apply HMM. So we usually model a 3-state left-right HMM. 3-state. So whatever unit is, we always model as a 3-state, beginning, intermediate, end. So let's say we have model. Let's say we model F phoneme, F phoneme, like, and then we can model as F beginning phoneme state and F intermediate phoneme state and F ending phoneme state, like that. And as it says, the left to right HMM, so it always have to go from left to right. It cannot go right from right to left. So this is the basic of the HMM in speech. Let's take a look at the example. Here, we want to kind of model one pronunciation, the one word. One word can be broken into phoneme U, and then another phoneme wa, and another phoneme n. So each phoneme, we model three-state left-right HMM model state, and as one is kind of the consecutive of the sequence of the W, AH, and N, those phonemes, three phonemes. So we kind of concatenate that phoneme state. And but you don't know. What you know is that you are given X. The vector representation of the X, and then each time you want to find what the HMM state is, and overall, when you're given here X1 to X13, you want to find the most probable HMM state rather than this is the kind of your problem. And other things that you have to model how the relationship between the state and observation. Here, X is observation of the mouth spectrogram feature, and then what's the relationship between that? People in the history, people normally model that this probability with the Gaussian mixture model, but recently people started using the deep neural network, and they use fully connected neural network. They sometimes model with the recurrent neural network. They sometimes use some time-delayed neural network or convolution neural network. Yeah.
So this hidden Markov model is out, but observations.
Mhm.
So also this has a, if you pick up a vocoder, listening to what it sounds like with the like you could
Mhm.
put in phonemes and cut it out, but
Yeah, phoneme. Yeah. Not vocoder. You have actually, when you model this, you have your training data, and then your training data, you kind of collect the statistics of the P of, so this feature and given by this S, what is the collection of that? And then normally people do is Gaussian mixture model, but if you flip between P of X, P of S given X, you can easily kind of model with the deep neural network, discriminatory, you can train model. Yeah. Any question? And then in speech recognition, the observation probability is modeled with the Gaussian mixture model or deep neural network model. And also state propagation, which is stationary. Normally people found that you don't need to care really about what the probability, state propagation probability. They kind of, they start with just fixed random 0.5, 0.5. They fix that, and they normally put a lot of effort to model of this probability. And that's just kind of the empirical study. And since starting using deep neural network, they have seen a lot of improvement recently. As you see in the graph, around 2012, people started using deep neural network for the emission probability, observation probability, and then word rate, which is the opposite of the word accuracy of the speech recognition, is getting dropped down really significantly. And you can also start from the phoneme level HMM, but definitely you want to recognize a full sentence. So you can expand phoneme level HMM to word level HMM with help of lexicon. And also with the language model, you can expand and composite the kind of the most probable kind of the graph from the word level to kind of sentence level HMM state. So basically with HMM, you want to find the HMM state, most probable HMM state that is corresponding to word sequence of the in the speech. And then we putting into one diagram, we can visualize this way. And rather than using just pure waveform, you can use X here, the mass spectrum. Feature extraction is just mass spectrum processing. And then decoder here, the acoustic model is the, as you here, this all the kind of combination of this probabilistic modeling, we say usually acoustic model. And then we also build lexicon to expand from the phoneme level HMM state to word level HMM state. Also to address kind of the word the probability of the word sequences, we use the language model, and then we can kind of the search through the whole sequences. So this is the HMM system, and then as you see, those are three model of language model, lexicon, acoustic model, are three main model in HMM-based system. Normally, people are optimizing each model separately. Language model, as you learned last week, language model is kind of the usually kind of the, you can build language model with Ngram, or you can use also neural network, but it's just use just use pure text, and then it tries to find what's the next word sequences given by the current word sequences. And lexicon is kind of the table that describes that each word has this kind of the phoneme sequences. So it's kind of it's not statistical model. It's just usually kind of the human labeling kind of code book. And acoustic model is that you can use the GMM or DNN as an option. But here, as I said earlier, people normally optimize this model separately. So it doesn't kind of optimize the kind of the overall problem, which is the P of W given X. Rather than, for example, acoustic model is trying to find what's the best kind of modeling of the P of X given Q. So sometimes, yeah, even though you have really good model for acoustic model, that always does not translate to the best performing speech recognition system, because those are kind of the there are some broken connection between each model. And as I said earlier, to model this for DNN, training DNN, you have to know actually, if you want to train the DNN, you know what's the S1 is then given what's the X1, right? S1 is the HMM state at the time, this time one here, right? And to get that information, you need some alignment. And because at the time one, what's the actual ground truth of the HMM state? You should know that, right? You should have that, then you can model that. But it's very hard to, just starting from just pure labeled text, it's hard to kind of define what's the time one HMM state, right? Yeah, it's very hard. So people are normally using this HMM system to find the maximize the alignment process, and then that gives with that alignment, you try to model the observation probability with that iterative loops. You try to find some this alignment seems okay, and then now try to find the best performing DNN model which recognize the P of X given S. Yeah. All right. So this is HMM. Let's go to the end-to-end ASR system. End-to-end ASR system is pretty different. It's just direct modeling of the P of W given X. It just tries to maximize W, most probable sequence given X, with just one model. Here, you use the neural network model. And this can be seen as a kind of the sequence-to-sequence problem. If you kind of took the NLP lecture last week, there has been a lot of the language model success. Actually, the machine translation and summarization or question answering with just language model, it gives a lot of success recently with the sequence concept. And people are also, okay, let's also start using this way. Let's kind of model sequence concept in speech recognition. There are three different ways to use this end-to-end ASR. First one is the connectionist temporal classification. And the second one is the attention-based encoder and decoder. And third one is the RNN transducer. And I will go by one. And the first one, CTC. CTC is very simple. You have X, the feature, and you kind of you have higher representation with the encoder. Encoder is usually just neural network. it can be RNN neural network, it can be fully connected neural network, it can be convolution neural network, it can be any type of neural network. With the embedding H, what you want to do is that you want to find most probable kind of the phoneme state, phonemes, or you want to find the character rather than HMM state. Here, there is a assumption that is the P of Y1 given X is independent with the P of Y2 given X. So each output is independent. Each output is just dependent what the feature is and then at the time. And how CTC works is it tries to find the most probable kind of the CTC output. But even for hello, it can be very different kind of the sequences, right? With introduction of the blank, it can have to represent the hello, it can be H blank E blank blank LLO or HE blank LLO blank blank. There can be a lot of alignment possible with this modeling, and how it kind of train the model is okay. We try to optimize this model to kind of maximize total probability of this alignment given X of X and the label sequences. And here you don't need actual alignment. You are just marginalizing overall possible alignment. So you don't need alignment here, actual ground truth alignment. The model can kind of address that in the model side. So it kind of gives us a lot of freedom. So you don't need lexicon as well. You can just kind of you can estimate the character sequences from the speech waveform, or you can actually estimate word directly as well. So it gives us a lot of freedom. But here, as I said earlier, there's some limitation because when you estimate the output, each output at different time are independent of each other, conditioned on the given feature. So it means that it doesn't capture the dependency of each kind of the phoneme or character dependency in the words inside the word, inside the sentence. So with this kind of model, it's hard to kind of capture the sentence level kind of the representation within the model. It only kind of captures the mapping from feature to certain unit of the sound or phonetic unit. However, this is very simple to use and simple to train. And also, sometimes people are using language model, external language model, to rescore the most probable sequence of the words or sequence of the characters like that. And then with that, they can see huge improvement. Another type of the end-to-end ASR is the attention-based encoder and decoder system. 2015, William Chen published the Listen Attend spell. In here, you will see the encoder. Encoder is pretty similar to where in the CTC, and then the important module is here the attention. The attention is here the kind of cross attention between the encoded frame and the output. So attention kind of guides what encoding frame you should target to estimate the current output. attention it can be seen as kind of the some HMM model similarly, but it's more kind of it can attend every kind of state as well. So it can or different phonetics unit, and so it's not left to right HMM. It can kind of go over. Yeah, it can look at the very different way. Yeah, opposite to HMM. And then here the decoder is mostly like this speller is like a language model. So it can with the attention guidance, it can kind of generate each word at each iteration. And with attention graph, you can see that how attention helps the estimate the output. If that attention works really well, you will see the monotonic graph here between the output sequences and then encoded frame. Cool.
I had a question about this slide.
Mm-hmm.
When you wrote that X1 up to XT goes into the model, is that all at the same time, or should I just think of X going in the encoder?
Here XU.
Yeah.
Yeah.
So XU goes into this step?
Yeah, XU can go into the step. Yeah. X1 to XT, it can go. So it depends on what encoder type you use. It can, if you use like RNN neural network, you can kind of input kind of every frame by frame, or you can also fully connected neural network. You can kind of you can see whole feature as well. Yeah, yeah. It depends on what encoder is. Yeah. And then, as I said earlier, the attention should be monotonic because speech is also monotonic as well. But people are talking about that the difficulty of training this like attention-based system in the beginning. Usually, the attention is very tricky to train the model. So sometimes people are using another auxiliary model which kind of give us a guide of the alignment, and then with that auxiliary model, you can easily train the attention-based encoder-decoder system. And the final one is the RNN transducer. Here, the attention-based system, it requires to decoder see whole encoded frame to generate the output, which means it cannot be. It's hard to work as a kind of online manner because it has to see whole sentence. It can always work as a offline. But most application works as an online speech recognition system, and so they're going back to the CTC model. CTC model, it generates the output at each time. It always just conditioned on its current encoded frame. And all right, but CTC, as I said earlier, the CTC lacks of the language model, which captures the kind of the overall language sentence in the sentence. So Alex Graves, he kind of give an idea. Okay, let's put another language model network along with the encoder, and then we kind of combine together with encoder output and then language model output to generate the current output. And for example, let's say I said hello, and then encoder kind of generate the frame, and then prediction network start with the beginning of sentence, and then this joiner network combine the encoder vector from the prediction network and the encoder, and then it tries to estimate what the current unit. And next time, the prediction network works as kind of the language model. So it is conditioned by the previous output, H, and then it also keeps the generate some embedding, and then with encoder gives us some acoustic embedding as well. Or with joiner, with the combination of the language model embedding and then acoustic embedding, it generate the next token, here E. With that way, yeah, it is similar as the CTC, so it can also generate the blank token as well. And HLO. And finally, if it has the end of sentence token, yeah, it can finalize the final output. So this is a transducer. So far we kind of reviewed what is the CTC, what is the attention-based end-to-end model, and lastly we cover the transducer model. Any other question? All right, we have 10 minutes. I will go quickly. So I want to kind of give you some recent idea evolving around the end-to-end ASR system. The first one is tokenization. You can use the character, you can use word to as a unit of the token, which are from the output of the neural network. But people find that the subword unit, which is kind of between word and then phoneme, and they kind of this way they find better performance with combination of the neural network and augmentation. This guy, the Daniel, he kind of interned at Google, and at the time he was not from the speech area. He was from, I guess, he's from this computer vision area. And then computer vision, usually you mask some input and then you try to recover the image. That's very common. And then he also tried that way in the speech recognition. So in the mass spectrum, he masked the time region and then frequency region, and sometimes also he kind of warp the time wise and kind of shrink or expand in the time region. Yeah, with kind of the distortion, intended distortion. Actually, the model trained really well, and then it gives more it gives more robust speech recognition system. Also recently, that there is a attention all unit. You already know that this paper, and yeah, people are applying this ASR. People are applying this transformer system to ASR. Transformer has the self attention and multi-head attention. It can kind of it can allow model to capture the kind of the dependency inside of the input. So here the speech input, you can kind of dependency in phoneme level, kind of the dependency, or kind of the word level dependency inside of the acoustic environment, acoustic space. And yeah, also on top of the transformer ASR, people are using convolutional neural network in the front end, and then they found that the conformal ASR encode really well for speech signal. And then a lot of the global company and then researcher, academia, and they are started using the conformer recently. Also, as I said earlier, the attention-based encoder-decoder system, it is hard to make the online system because the attention has to kind of access the all from end to end, its feature and the end-to-end output. And then to address this issue in online environment, yeah, they kind of limit the search area region to make the online way, and this is kind of the monotonic cross-head attention, this MoCA, and And also people are trying to train ASR system with offline and online together, also, but sharing the model for each different mode. And then it has been also success as well. And as I said earlier, with conformer, we found that or conformer or transformer, it can really capture the input signal of the speech. And once the model generates the embedding, it conveys a lot of meaning. Which can be very useful for other tasks besides on the speech recognition task. So sometimes people are using this transformer output embedding for the translation, for speaker activity detection and language detection. So yeah, you can kind of once you have this kind of encoder, good encoder, you can train multiple tasks in one neural network. And yeah, this has been success. Recently, the Whisper from the OpenAI, it can do many jobs. It can transcribe multilingual speech, like from English to Chinese, Korean, Vietnamese, and even I don't know some Swahili or yeah, and a lot of language it can transcribe as well, and also it can detect the language as well. It can also translate, even it can translate from English to other language as well. Yeah, so the joint modeling has been a recent trend in end-to-end ASR, and also with this kind of end-to-end neural network model, people are making bigger model with the scale data, and then with the historical record. Last year the Whisper model is the now 1.5 billion model. Even 5 years ago, the model was almost 100 times smaller than this 150. Yeah. So it's amazing. Maybe we will see more improvement this year. And that's about it. And to ASR, do you have any question? Mm-hmm. Mm-hmm. They use same model parameter, and the same model parameter, depending on your input language, and then you can transcribe. Yeah. But it has, or I believe that it has the language identification inside of the model, and then it kind of guides what to transcribe. Yeah. All right.
Does Whisper use conformers too?
I believe that they are just using the normal transformer. Yeah. Normal transformer encoder and normal transformer decoder. Yeah.
Is Whisper using the AAT? Are they using
It doesn't work live. Yeah.
It doesn't work.
Yeah. Attention-based encoder and decoder, just pure attention-based encoder and decoder. But it has model like voice activity detection. Using this model, it kind of and it can end the point where to end, and it can restart the transcribe, but it doesn't kind of do in online patient. Yeah, it has to process a whole feature at one time. Yeah. All right, this is a homework. With HMM model in 27 pages of slide, you have to guess what would be the most probable state when your spouse sends this kind of the sequence of the emoji. That's the homework. And then Other one is when you have 1 hour of label speech data, how do you want to train speech recognition system? So very limited system, what do you want to do? And also to make noise robust speech recognition, what can you do with the modern end-to-end speech recognition? These are homework. I am looking forward to hearing innovative idea and very good answer. And next one, can you, who can cover this one?
Sure.
Yeah.
I can just read them out.
Yeah.
Did not actually.
Yeah, this is homework from the last lecture. Phoebe will kind of be.
So I'm just going to read these out. So the question was, recurrent networks exploit translation symmetry in text. What symmetry do convolutional neural networks exploit? And they do translation symmetry in space, since convolution is 2D in space rather than time. GPT-2 has a context window of 1024 tokens. GPT 3.5 has 8192 tokens. And how might this change the number of parameters in the model, keeping embeddings and number of attention heads and layers the same? So the number of parameters is going to scale as O(n) squared, where n is the context size. So if you change that up by that amount, it's going to be a factor of 64 times when you scale it up by 8 times. And finally, so why does ChatGPT struggle to perform arithmetic when it can write functional code? And this is because LLMs understand numbers and properties in a sentence, but they're not easily equipped to actually perform arithmetic algorithms on large numbers, which don't kind of resemble this text. So an example would be this. We also had fun at the beginning with it insisting that 2 was not an integer. So be careful with your maths homework. Cool. Thanks for joining, everyone.
Thank you, guys. If you have any question, also feel free to reach out to us. And this is today's lecture. We'll see you next time. And should I finish the meeting or?